problem, when you solve problems, is that you solve a solution for the Laplacian equation. But this is usually very complicated. Sometimes you don't have a solution, sometimes you have a solution, right? Or a closed form solution. I mean, we do a lot on the Laplacian or closed form equation. But if you go through like a first year grad school, of course it's E&M, right? The first half of the course is solving all the time. All the time. Yeah.
And then del
It's del dot.
Yes.
I know.
But there are two theorems in there that you should read through. I didn't go through the theorem. There is a consequence of space, right? The first one is, I think I mentioned it briefly, that if you take in space, if you take any sphere, right, and you average
it's a one form.
the potential around the sphere.
It's a K form. No, it is, because it takes in the vector.
Around the sphere S, S, right?
Yes,
It's going to be equal
it's
to the
a
value of the potential at origin. So this is why we already know for Laplacian. And you can also prove, remember at the end of lecture today, if we have a cavity, if we have a cavity here, the potential on the conductor is constant, say V naught, right? Then the electric field inside has to be equal to 0. Right? I did a more physical proof,
right, yeah.
right? But you can also prove it using the property of a Laplacian equation.
Yeah.
Who does it valid?
Okay.
Any other vision?
When you say the average equals the radius at origin, does that mean like radius from the
So this is the beauty of it, right? If you have in the region of free space, right? Basically, it's a property of the Laplacian. If the Laplacian of a function is equal to 0, right? You can go any sphere you want, right? Small, big, it doesn't matter. Average the value of phi over the sphere, right? It will be equal to the value of phi at the center.
Oh, okay, that's what
Might not seem useful now, but it will be useful later on.
Okay, but what is divergence again in terms of
In terms of physics, let's see. So let's forget about this for now. This is completely new for me. That's fine. But remember the definition of divergence of vector E, say, right? Is actually the limit of a flux over a sphere when you take the volume zero. So remember, if you have a flux of E over dA, right? I can break this down. I can partition my volume into many little differential volume, right? Right? So this is the sum over I of integral A over these differential surfaces. Right? And I think I showed briefly that this actually over the differential volume here is this limit is this. So limit that this is 0. This is actually finite. This is move my So this limit exists, and this is actually the divergence of it can be any vector, right? It doesn't have to be a vector field. Yes, of the flux over a surface. Right? If I just look at one element here, right? If I look at the flux over the surface, right? And I have the limit as I swing the whole volume, right? That is the divergence.
Why is that used? Or why would?
Why is this? Right, why is this?
What is it?
We do this in section 7B, we don't do this in section 7B.
It's a scale.
We don't know what divergence.
Well, because it's not a, because there's only part of the roof.
Then you can have a differential statement, right? So this is completely equivalent, right? Use this as a...
Isn't x1 the direction?
It's completely equivalent, right?
Those are unit vectors.
Oh, makes it easier.
The first one is its
Yes,
cartesian.
so for example,
But
they
that's
also
the model.
That one's the gradient. And that one's the gradient.
Yeah.
And by this is a step, by making this step, we allow to write the Laplacian and the potential. Otherwise, you do not know, you do not be able to write this equation.
So the Laplacian is like the divergence of the gradient.
The Laplacian is always a scalar.
The Laplacian is scalar, yes.
Okay. Whereas the divergence is going to be a vector.
No, the divergence of a vector is a scalar, right?
Okay.
Okay, so divergent always act on a scalar, sorry, on a vector. Right? And then it turns into a scalar. Okay. You can think of this as a dot product between this in Cartesian units, right?
Okay.
This is just a dot product between a gradient and a vector, and it gives you a scalar. Right? And in the case of electric field, that scalar is just rho over epsilon naught.
But then why in, right under Cartesian, you have, no, above that? Yeah, right there. You have del phi,
What
and
is
then you have,
ah.
and then you have, that's a vector right there, right? Because it's x hat, y hat.
This is actually a statement for a gradient. So a gradient of a scalar.
Okay.
This is a gradient of scalar.
Okay.
Turns it into
Take a scalar, it turns into a vector.
Okay.
Right? Divergence, take a vector, turns into a scalar.
Right.
Okay, and Laplacian is a combination of the two. Right? First you take a gradient of a scalar, and then you take a divergence of that.
Okay.
Right? And then it becomes Laplacian. Right? So in the case of E&M, the Laplacian of as long as this potential is equal to minus rho over H1 with a minus sign. Right? Because electric field is minus. Minus the gradient potential.
So the deltas there, I don't know what letter that is really, those don't act on phi the same way, each one, but so the
yeah.
del squared thing is just kind of a notation that denotes Laplacian. It's not actually like del squared.
Yeah. So, but you know, you can
Because
just
they
remember
each
that.
act differently.
Right. If you just want to remember formally, notation-wise, when you write something like that, then it's just
A Laplace. Or okay, yeah.
this is the operator acting on something.
Mm-hmm.
Think of this as a machinery, right? You input a scalar, right? And the machine acts on that scalar, and it gives you another scalar. And the way it operates is by performing all this evaluation. The gradient is something else. It's written like that. Right? If this is a machine, right, then it takes a scalar, right? It takes a scalar and acts on the scalar with this thing here, right? And then you get a vector. Then you get here, you get if you add on 5.
And what is it doing if I is it just taking the, like, if it was, if I was a volume or something, Is that how this step goes?
Say it again.
Because I don't get how you go from the limit of this integral thing to
yes.
the divergence.
You can show that this, if this limit exists, right? Then this operation, right, which is defined, which is, we call it divergent, right? Then this becomes just
Do the partial derivatives make the limit of the volume zero?
say it again.
Do these partial derivatives are like they're making it sort of zero? Is that what it's doing?
No. Meaning that if you evaluate this integral, you get that. Right? I think I mentioned this briefly in the lecture. I was just trying to show that the limit exists. Because the limit exists,
I guess it's 4 dimensions. It depends how many.
when the limit exists, that just becomes, you can just you can do that. I don't know how to forward the calculation, but that limit becomes just a Ex.
No, I thought it was a normal.
Right? And then you have another one, y.
It's normal.
Y. Dx
Like you
dz.
see, like infinitesimally sound planes at that point. The tangent plane
dy
is normal.
dx.
The gradient is normal. The tangent plane.
Right? And another one was dec dz dx dy. This is all just volume element, and it cancels that volume element. And you're left with you're left with the sum of these three terms, right?
Yeah.
And that's the definition of the divergence. If this is confusing, follow line by line derivation in this it's
And why in the first place do you want
When you want to curve x, y,
here.
in
Because then I want to express
in directions.
this integral here, then it becomes, if this exists, right, divergence of E, then this expression becomes dV times divergence of E, right? Sums over I. In the limit when dvi goes to 0, it's become an integral of, like, I'm always in place, like, this is a this is your gospel. Or this is just, no, this is not the gospel, this is just the left hand side of the gospel. Okay. Left hand side of the gospel, dA becomes determining a surface integral, right, into a volume integral. Surface volume dV. And then the right hand side of the cosmos gives you 1 over epsilon naught. Right? Remember this?
Yeah.
And this is a general statement. It can be of any volume. I can make my volume whatever I want, right? So in order for that to happen, the only way possible is if the integral is actually the same. Right? It can be anything. As a result, the divergence of E becomes rho over epsilon naught. Right? This is a machinery to turn an integral statement into a differential statement. This is confusing.
It's just there's so many like
I know,
integrals and
yes.
circles and
I
like
should-
dots.
Fine, totally.
And it's like mixing the different Gauss law with the number, and they're just, I don't know, I guess they're just.
Okay, let's do it again. You want to do it again?
Yeah, I can.
Okay, briefly, right? Briefly. I'm going to try this as quickly as possible. take any surface, right? I want to evaluate this integral over the surface f. I'm calling it f because I don't want you to do, this is general, it doesn't have to be electric field, right? As long as the function is relative. Since this is a flux over the surface, right? I can partition the surface however I want. I can cut it in half. I can cut it in half again, right? I'm not very good at 3D drawing, but I can cut the surface in two at the volume, right? Partition it in half, right? Partition it in half again, right? Okay. Then this integral is basically the sum over all the volume of all the closed loop flux over that volume. Over SI. Just think about it. If I just divide it into two, right? So this is S1, this is S2, right? The part of the flux that goes through the boundary, right? The flux is if it's negative for S1, then it's exactly positive for S2, right? This flux cancel, right? So then this integral here is just the sum of the closed loop integral between S1 and S2. And I keep on doing this. I mean, divide it again in another half, right? And so on. Right? So when I partition this, so I have n volume, n different boxes, right? The total of that integral is basically still the same original surface integral. Right? Okay. So now, if I take this, process all the way to the limit when I goes from 1 to n, right? And I take n to infinity, right? Then basically I have to evaluate integral like this, integral of SI f dA, right? When SI goes to 0, right? When this volume goes to 0. Okay? And of course, if this goes to 0, this integral goes to 0 too. But if I divide by the volume, right, my claim is this is finite.
You're defining all of the tiny fluxes?
Yes, if I add all the tiny fluxes, if I just take one of these volumes here, right? If I just orient, for simplicity, if I orient the box in the Cartesian, aligned with the Cartesian coordinate, right? So this is x, y, z, right? And then say the flux through y, right? The flux through y, you have this part of the flux on the left wall, and then you have another part of the flux to the right wall, right? Okay. And the total flux is basically, you can convince yourself, well, first you have, is F at y times the area of the wall, okay, which is dx dz, right? With a minus sign because the flux is inward. And then there's another flux, which is the plus sign, is f of y plus dy, also times dx dz. Right? But this difference is just df. This is the factor right away, right? This in the y direction. This is dfy dy times delta y, right? This difference to a linear order is just equal to that. times dy times dx. Okay, and I can do the same thing. Here I'm just doing it in the y direction. I can do the same thing in the x direction. Then I get also a difference, right? A difference from one wall to the other wall, right? Then I get a term like df x dx del x, right? Times the area, and the area in this case is dy dc. Right? That's the flux along this direction. But there's also another flux along that direction. And if you do it right, it will give you have c dz times delta c, and the area is going to be dx dy. Okay? And as you see, then the whole thing just becomes df x dx plus df y dy plus df c dc times dx dy dc. Okay? And this is just the differential product. Okay? So, and that's just equal to that integral. Right? It's just equal to this integral. 1 plus I dA. Right? Okay? So, and if I divide by dvi, then this is just equal to 1. Okay?
Oh.
Right?
You did it.
Yeah, and then you define this as the divergence. You define just this whole integral. This integral here, which is in the end just equal to that, because the dv cancel, right? This is then just equal to you define dv equal to the divergence of m. Right? So once you have this definition, I can go back to the original equation, right? Times dA, right? And this is just equal to the sum over I, okay, dvi times the divergence of m. Right? Okay? And in the limit, when this goes to 0, then this becomes an integral. This is just expressing the surface